Hi, today I'm going to talk about our work, Interaction Visual Transformer for Egocentric Action Anticipation. I'm Debaditya Roy, and I did this work in conjunction with Ramanathan and Basura. In Egocentric Action Anticipation, we observe a video for an observation period, and we have to predict the action which happens next. Here, the observed action label is not available for us during inference, which means we have to understand what is currently happening, and based on that, we have to predict the action which will come next. The applications involved are autonomous driving, where we have to predict what other pedestrians or cars are going to do next so that we can plan our next move, and assistive robotics, where a robot has to predict what the person is going to do next so that it can help him or her in their tasks. One of the key observations for predicting the next action is to recognize objects and context. Here we see that once the spoon is recognized in the vicinity of the sink, which is the context, the correct action wash also moves up the ranking, which means that if we recognize that an object is in a particular context, we can predict what are the future actions that are possible with that object. Also, another important observation is to predict where the hand will go next, because predicting the future motion of the hand is going to help us identify what the next action is going to be. So essentially, we need a way to identify key human-object interactions. So the challenge is to capture relevant objects and interactions from current action that can contribute to future actions. However, this is a challenge as there are many possible objects with which the hand can interact, and we have to determine which is the most important interaction that can contribute to the next action. Hence, existing works use manually annotated hotspots and trajectories. However, these are not scalable to large datasets. Hence, in our paper, we only use the information from the captured objects and interaction. Here we detect a glass, a bottle, and the hand. And we can see that since the person is pouring water into the glass, the next action will be drink water. So, given that we can detect the hands and the objects in the ongoing video, how do we model the interactions between them? Here, in our paper, we propose an interaction region modeling framework, in which our novelty is to model the interactions as change in the appearance of hands and objects. For example, here we see that the hand is holding a chopstick. Now, there is a orientation of the hand which changes when it interacts with different objects. We use this change to determine what object is actually interacting with the hand. Here the hand is holding the chopstick, which would determine that the hand is in a certain pose. If the hand was holding a glass, it would be in a different pose. So we take a cross-attention based mechanism where the hand object which is detected and the patches of that, we use cross-attention to compute the change in the hand object with respect to each object token. Whereas for each object token, we also see how it is being influenced by the hand and the other objects. Again, we model this using cross-attention in every frame. Both of these refined hand and object tokens computed using cross-attention are used as interaction tokens or interaction region tokens. Apart from the interactions, we also need to understand where these interactions are taking place, which is the context. For example, here we see that the person is opening the sauce bottle. With the context of the pan and the cooking hob, it might be that the person is going to pour the sauce into the pan. Hence, we need to infuse the context into the interaction regions as well. For this, we propose a new trajectory cross-attention mechanism to infuse the interaction regions with the context in each frame. Let's recap what is trajectory attention. Trajectory attention aggregates information along implicitly determined motion paths. So it tells what the object is interacting with in a current frame and what the object is going to interact with in the subsequent frames. We also use this mechanism to find what the interaction tokens are interacting with in the subsequent frames. So for this, we compute the spatial cross attention between the interaction region tokens in each frame and the environment keys. We do that in each frame in order to find out the best possible location for the interaction trajectory. Once we find out the best possible location in each frame, we pool all the interaction region tokens across the frames in order to form connections on how the interaction region tokens have interacted with the environment. So the goal is to basically obtain a video representation that incorporates context-infused interaction tokens. So our total architecture looks like this. We first find the interaction regions modeled using the refined hand and object tokens. Then we go to context infusion, where we infuse the context from the environment to the interaction regions. And finally, we use this context infused interaction tokens and the video patches to compute an interaction-centric video representation. Now, this interaction-centric video representation contains the information of both the video and the interactions that are happening in each frame. We use this interaction-centric video representation to anticipate the next action. So we evaluate our method on Epic Kitchens 100. This is a very large unscripted egocentric data set, which has 3,805 actions, comprising 97 verbs and 300 different nouns. So these nouns are objects which we interact with. So our method InAViT, which does interaction modeling and trajectory cross attention, performs much better than the state-of-the-art methods, even recent methods which involve intention conditioned action anticipation. And we also show that common video transformer methods like MotionFormer and object-centric video representations like Orbit, which only focus on object-to-object interactions in frames, perform slightly worse on verb, noun, and action mean recall. The reason for using action mean recall is because there are thousands of different actions. So even if we are able to predict the next possible action within the top 5 predictions, it's still a good result. Even on the public leaderboard for Epic Kitchens 100, we outperform the second best model by 3.3%. And we see that InAViT performs well across unseen and tail actions as well. We take another dataset called EGTEA Gaze Plus. This has 106 actions with 29 verbs and 51 nouns. And we see a very solid improvement of 81% in top 1 accuracy, performing very well compared to the next best abstract goal method. So this shows that InAViT not only performs well on large dataset, but is able to improve across the board. So when we study how each of our component performs, we see that interaction regions along with context infusion work quite well. But the biggest boost comes from interaction-centric video representation. Here we also compare the different interaction region modeling strategies. One is where we aggregate only the object refinements and the hand refinements over time. And in the other where we take the union region between the hand and the nearest object. We see that the performance of the the interaction region modeling strategies is pretty similar, but our proposed spatial cross attention mechanism for modeling the interaction region works the best. Finally, we see some qualitative results. Here, we see that even if the bounding box does not exactly localize the hands and the objects, we are still able to predict the next action, which means that even if the camera moves around where the object detection might not be very accurate, we are still able to predict the next action if the detection covers the region around the hand. Through this work, we have seen that learning the relevant interactions is vital for action anticipation. And the way we model interactions as hands and objects changing each other's visual appearance aids in the learning of these relevant interactions. The region and the context also provides vital information for accurate action anticipation. And finally, interaction-centric video representation is very effective at action anticipation, and it outperforms the state-of-the-art models by a large margin.